Hey everybody, we're going to go through the first Chem 8A exam in the fall of 18. What we're going to do first here is we're going to fill in any hydrogens not shown and give the molecular formula. So the main thing to remember is that carbon can only make 4 bonds. So we look at this first example here, we see that this carbon on the benzene ring has 3 other bonds, so it has 1 more hydrogen. Same thing for here, here, and here. These 2 carbons already have 4 bonds as annotated by those individual lines, so no hydrogens to add. Heteroatoms like nitrogen, the hydrogens are explicitly drawn, so nothing more to add. This carbon here has 3 bonds that are shown, 2 to carbon, 1 to nitrogen, so only 1 hydrogen remains. Up here, this carbon has 2 bonds to carbon and 1 bond to another carbon, hydrogen. This gives us a total of 6 carbons in the ring, 7, 8 from the other ring. We can count at the total number of hydrogens altogether. We have 1, 2, 3, 4, 5, 6, 7. And then 1 nitrogen. On the next example, we have all carbon-carbon single bonds in the ring. This carbon that's connected to a chlorine also has 1 hydrogen. 1 hydrogen. This has only 2 bonds explicitly shown, so the remaining ones are both hydrogens. And then same one here. These are all CH2 groups. We have 5 carbons total. We count all the hydrogens that we've added in, 2, 4, 6, 7, 8. And then we have the 2 chlorines. If we did this right, we should be able to use the degree of unsaturation formula that you guys have since learned. And it should work out that this compound here, though this is not part of the question, has 1 degree of unsaturation. So that means that you have 2 less hydrogens than in the typical molecular formula, also accounting for the fact that these chlorines are going to occupy the space of a hydrogen. Moving on, because I'm getting ahead of myself. We have part B. We're going to draw Lewis structures for each molecule. We're going to add lone pair and formal charges where appropriate. So the key thing here for drawing a carbonate molecule is to first count up the valence electrons. You don't want to skip that step. That would be silly. You have 4 valence electrons from carbon. You have 3 times 6 valence electrons from the oxygen, plus those 2 from your charge there. So that's 18 plus 2 is 20, plus 4 is 24 electrons total. You start by drawing your central atom carbon that's connected to 3 oxygens. You know it's your central atom because it's written first and because carbon can make more bonds than oxygen. And there's less of them. There's 1 carbon, whereas there's 3 oxygens. So you start by drawing your single bonds to the oxygens. We're then going to add in the remaining 24 minus 6 is 18 electrons. So here we go. Right now we have 6 that are drawn, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now this right here actually is a valid resonance structure if we put the formal charges on there. The formal charge formula I'll go through, I think it's more appropriate on the next page. So for right now, I'll just say simply when oxygen has 1 bond, it's negatively charged. So all 3 of those are negatively charged. When carbon has 3 bonds and no lone pair, it is positively charged. And again, we'll go over the formula for that, I believe, on the next page. So the other resonance form that you might have come up with, or the other Lewis structure you might have come up with, is one where you have less charged atoms. You can go through the same individual steps where you have the 3 single bonds, but instead of placing all of the electrons around all of the oxygens, you might stop and say, hey, let's have one of those lone pair on this oxygen to the right serve as a pi bond. And what that does is it shares those electrons between carbon and oxygen, so those 2 atoms are no longer charged, and we just have, once again, a -2 overall net charge. So either of those structures are okay. Either way you slice it, you'll find that the central carbon atom, this guy here, has 3 electron groups around it, or rather it's bound to 3 atoms. So that means that it's going to have an sp2 hybridization. And if you think about it, sp2 is actually spp written a little more simply, and that's how you can remember that there are 3 electron groups because those are 3 letters. The name of the geometry associated with sp2 is trigonal planar. So while I didn't draw trigonal planar geometry up there, it's implied because it's sp2, and so trigonal planar geometry is one where you have 120-degree bond angles. Okay. The next example is chloroform. We went over this one together in lecture. This has 4 valence electrons from carbon, 1 from hydrogen, and 3 times 7 from chlorine, and we get those from the periodic table. So that's 21 plus 1 is 22, plus 4 is probably 26 valence electrons. We start once again with our central atom carbon, and we do individual, or rather single bonds to each atom that we see. That takes care of 8 electrons. So let's add in the rest: 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Now, each atom in here has the appropriate number of bonds, so there are no charged atoms. This one is very happy as is, so no need to do any double bonds or make any other changes. You notice that the central atom carbon has 4 electron groups around it, or rather it's bound to 4 individual atoms. So this is going to be sp3 hybridized. sp3 is the short version of spp. Those are the different orbitals that needed to be combined in order to make an sp3 orbital, and you can see that there's 4 of them, and that's how you can remember that these are 4 electron groups for sp3. The best way to spread out those 4 electron groups is in a tetrahedron. The geometry is called tetrahedral, and a good way to remember that is that this prefix tetra means 4, so that's the trend. Continuing on with hybridization stuff, we have next prednisone, an anti-inflammatory, and methyl azide. So what we have here for hybridization-wise, we're looking for, first, I'm going to look for sp3 hybridized atoms. Once again, these have 4 electron groups. This carbon right here is actually a CH3 group, so if it's involved in just single bonds to carbon and it has all 4 of them, that's your 4 electron groups, and that's sp3. Another example of an sp3 hybridized carbon would be this carbon here. We can explicitly show the 2 hydrogens if it's helpful. You can see that it's bound to 2 other carbons as well. And this is going to be sp3 hybridized. We're going to move on to this oxygen. We add the lone pair because that's going to be helpful. And we see that it has 2 lone pair, 1 atom connected to hydrogen and the other connected to carbon. That's 4 electron groups total, so this is sp3 hybridized. There's one more sp3 hybridized atom, and that's this carbon atom here, methyl azide. There's 3 bonds to hydrogen and 1 bond to nitrogen, so that's 4, and we get sp3 geometry. Next, let's go to the purple team. We're going to look for sp2 hybridization, and we're going to be looking for 3 electron groups. An example would be this carbon of the ketone. It's connected to an oxygen, a carbon, and a carbon. This is going to be sp2 hybridized. This carbon here is connected to a hydrogen, a carbon, and a carbon. This is going to be sp2 hybridized. The oxygen of this ketone has 2 lone pair and a bond to carbon. That's a total of 3 electron groups. That's sp2. This nitrogen here in methyl azide has a lone pair, a bond to carbon, and a bond to nitrogen. So that's 3 electron groups. This is also sp2. And last but not least, this nitrogen has 2 lone pair and a bond to a nitrogen. That's 3 electron groups, and that's sp2. If you're having a hard time adding lone pair, I suggest that you work your way back from the number of valence electrons that it has. You should have a similar number to start out with, meaning never mind. If you're having a hard time coming up with the number of valence electrons, actually an easier tool for nitrogen is to remember a couple of standards. So ammonia, for example, is an example where nitrogen has 3 bonds and 1 lone pair. You'll notice that when nitrogen is positively charged, it has no lone pair and a positive charge. And then on the opposite end, when nitrogen has 2 bonds, it has 2 lone pair and a negative charge. Finally, we have 1 atom left over. This nitrogen atom here in the middle has 2 electron groups. It's just bound to 2 nitrogen, so it is sp hybridized. And that's it for page 1.